Hi, this is Bill Punch from Michigan State University with another video in the series of videos on the topic, the practice of computing using Python CSE 231. Today, for the first time, we're going to talk a little bit about efficiency and how we might best measure efficiency for a computer algorithm. Let's get started. So the first thing we'd like to think about when we're talking about efficiency is, shouldn't we just measure how long the algorithm takes? But that is almost clearly not the best solution. Too many things depend on how long the amount of time a particular algorithm might take. The computer it's running on, its operating system, the programming language we're using, its optimizations, and so on and so forth. All those would affect the time and make it very difficult for us to compare two algorithms to see which one was better, more efficient. What we'd really be interested in is an algorithm so that we could measure the amount of work it has to do as it grows. Because we would like to know, as an algorithm has to do more and more work with more and more data, how much more time does it take to do that work as the size or the effort that's required grows. And so in the end, the thing that we're most interested in is the ratio between effort and time required, and that is going to be the same across platforms. That ratio is going to be really useful to us. Let's take a look at just a sorting algorithm. A sorting algorithm is used because this is a classic way to try to measure the amount of effort to the time taken, where effort is going to be measured by the number of things that we have to sort. So this particular algorithm is called a selection sort, and it's probably easier to show it to you than to talk about it. Here's how it would work. What we would do is we would make a pass through the entire list, and we'd find the smallest element, and we'd swap the smallest element with the first element in the list. Then we would do, again, the same process. We'd leave that very first element alone, but we'd make a pass through the list, find the smallest element, swap it with the essential beginning of the list, and do it again. Pass through the list, find the smallest element, swap it, in this case it's in place, until we've gone through the list. Here is the algorithm for doing that. We have an outer loop which goes through one at a time, finding the smallest element and putting it in place, and then the inner loop that looks through the loop to find the smallest element. And if we apply this to something like a list of elements, we get the ordered list to come out. Let's try to go through and do some comparisons. What we're going to do is we're going to measure the time, we're going to import the time algorithm, and we're going to make random integers. And what we're going to do is generate lists of random integers in the range from 50, 500, 5,000, and 50,000 elements in the list. We are going to set the start time, run the selection sort, and end the time, and then print out some information. Now this takes a little bit of time, so rather than sit here for 3 minutes while it runs, this is the results I got when I ran it on my computer for the size of 50, for 500, for 5,000, for 50,000, and these are the number of seconds it took to run this stuff. And if I put this in a table, 0.003 to 0.02 to 1.55 to 161, every time I multiply the size of the data by a factor of 10, on average, the amount of time it takes goes up by a factor of about 82 on average. So for every 10 increase, I get an 80 increase in time. And I would say that as a ratio, at a roughly speaking approximation, I'd say that this was an n-squared algorithm. That is, for every 10 times increase, it roughly goes up by 100 times in time, right? 10 squared. I say roughly because we know that's not exactly right. It's a little better, but that's a pretty good indication of how things are going to change as the size of the data grows. Roughly a factor of squaring the number of elements that we put in. And it's this roughly speaking that gives us an idea about how long the algorithm would take to run, and we call this, typically when we summarize it, the BigO notation. And the BigO notation comes in these various forms, where the element in parentheses is the ratio information. So BigO of 1 means that an increase in data has no effect on time. BigO of log n means that as the data increases, the time increases by the log of n. Big O of n means that it's linear time. For every increase in the amount of data, we get the linear increase in the amount of time. Quadratic is what we saw in the selection sort. For every element that we add, we get an n squared increase in time. And then worst case scenario, right, if it's exponential. For every element I add, the time goes up by a power of its size. And if we were to plot these out, this is the kind of stuff it would look like. For linear growth, right, it's not so bad. As we increase the number of elements, this is the amount of time. But notice that something like n cubed, as the size of the number of elements grows, this goes up enormously. And something like exponential would go nearly straight up. These are bad growth characteristics for these algorithms, and so the big O notation gives us this rough indication of how bad the growth stuff will be. N log n, something like that. The question is, why is the selection sort n squared? And so it's worth going back and looking at it again. We have a nested loop situation. We have an outer loop and an inner loop. In the outer loop, for every single element I pull out of the list, the inner loop runs roughly for the n number of elements in the list. Now that's not exactly right, because we collect the minimum elements at the front of the list, and so we don't actually have to look at every element, but roughly speaking that. And so if I go through n times out here, and then every time I go 1 here, I go n times there, that's n times n, which is n squared. So algorithms that roughly have these nested loop situations typically run in something like n squared. Now it could be less than that, it could be more than that. It's 80 times, not 100 times in terms of how it grows, but still very bad. So when we talk about big O notation, we're talking about the fact that, roughly speaking, the ratio of adding elements to the algorithm changes the amount of time it takes to solve the algorithm in the following way.